Thanks. Talking about some relativity stuff. Okay, so yeah, it's quite fascinating about this theory as one of the theories that in the modern physics in our era now. So one of the fascinating things that you guys as a physicist want to check on. But then we'll focus on the SR and specifically the Yo Kian Yao. Specifically, you want to focus on the stable team. At PSO, I think we'll mostly about SR instead of GR. So let's say, okay, in the sense that we were talking about the flat space time. So we're assuming that now our space time is in space time. Okay, so it's one of the system again. But then I will explain what it means. Okay, so assuming that now, okay, in in the classical way, let's say hi to, okay, hello. Okay, so in the classical way, you were thinking about in the classical way, space, you were thinking about space and time is a different thing, right? Like X, Y, Z direction, the space itself and also the time itself is a different thing. And when you are dealing with the classical way, but then now we are try to see it as a single framework, single that the things that equivalence. We call it space time. Okay. So and also now we are talking about some counterintuitive stuff right? In the counterintuitive in the sense that because it's you are not experienced you are not experiencing like you are moving in the like very fast approach the speed of light. And then now because in our daily experiences, we are only not how to say, we are we are very slow speed compared to the speed of light. That's why we are the relativity effects of relativity is quite small, quite insignificant. That's why we see this and we go through. It's very counterintuitive. Okay, so okay, as usual, we are taking the big picture first. Okay, so I will go through the idea of it. And as usual, we will if I have the time, so we will go through the question. So uh, just to give you guys the idea of that, what what we are talking for today. Okay, so we are talking about we're talking one thing like let's say like last time we building with the classical mechanics, we will start with the kinematics, and we are moving on. And we talking about the equations, so try to describe the uh, velocity and others and the stuff that we're moving on the dynamics. From kinematics, we're going to dynamics. So we're talking about the force, the momentum and energy and that stuff. Yeah, okay, those kind of stuff. So moving on dynamics, kinematic to dynamics. Okay, so but there is a relativistic things. Okay, so and we're moving on the effect of it and how we can apply how we can like when you are dealing with the let's say you are the astronomer, you are the astrophysicist, they want to see how is it related to your career. Ready to how the relativity relative I guess, um related to that. Okay, the effect of that. And yeah, there will be stuff like that. And and also the last idea we want to reach the idea to GR. And if you have any interest, after I mean after the computation, or if you have the time and encourage also you can try to do some self-study or want to learn more about GR because now we are specific spatial relativity only. And going on to GR, you want to start with one equivalent principle, okay, the big kind of idea that grounded in the GR. Yeah. you want to, if you want to further investigate what is GR. Okay. As usual, if you have any questions, you can try type in the chat box, or if anything you are not agree with. As usual, right, as relativity proposed by Einstein, it seems like the people trying to study this paper and trying to develop that theory, that framework, and comes up with many paradoxes. But then you will see that you will see twin paradox, and also the twin paradox, and also what I call it again, ladder and bun paradox. Many kind of paradox appears when people trying to understand the spatial relativity, specifically spatial relativity, and you'll see that all of the paradox can reduce it, can be solved one by one. If you carefully study on spatial relativity, it's that kind of beautiful things. Okay, when you are doing with it, with the carefully Lorentz transformation, and we'll see what is about the Lorentz transformation after all. When you're dealing with relativistic stuff. Okay. Just an idea of what Einstein started with. It started with the let's say we want to start with the postulates. There will be two postulates that you want to keep in mind. It's one of it is all inertial frames. Okay, that's also why it's all about non-inertial frame or inertial frame. What is the difference of that from the classical mechanics? Yeah. Okay, so one of the postulates is all inertial frames are of inertial frame or reference are equivalent in a sense that physics law hold in one of that all of the inertial frame. Okay, as well if this physics law like Newton's law is applied in this inertial frame, and let's say for example, and also Newton's law also applied in another inertial frame also. There's one thing they want to thinking about that in mind. Okay, so because if for example, you're talking about non-inertial frame, the idea, if you want to talk about the non-inertial frame, the Newton's law is not applied because it will come in with a fictitious force. Okay. Something about imaginary force. So and also the Newton's law is not applied for that non-inertial frame. Okay. So another second postulate will be about speed of light in vacuum is the same in all inertial frame of reference. Okay. In a history, if you want to talking about the history stuff, why? Because it's quite counterintuitive. Like let's say you have you are on the train or you are on a plane, it's not rocket. See? Okay. Okay, you want to shoot a light. You have a light emitter, photon emitter. Okay, you emit a photon, a beam of photon actually. Light, okay. The light moves in the speed of light, okay, and also the rocket moves in the speed of v also. And from the Galilean transformation, okay, Galilean transformation. Okay, so Galilean transformation, right? So when going through this Galilean transformation, the speed of light in outside of the paper frame relative to outside the paper, which are C plus V. Okay, so the kind of Galilean transformation is talking about that in our mindset, in our intuitive. Okay, and then in that sense, like in Einstein postulate, we want to throw out, we want to come in, we want to keep the speed of light constant. Okay, and in fact, if we going to in details like in the theories, we found that the speed of light in constant quite actually comes up by naturally. Okay, and yeah, there will be the things second question we want to talk about. Yeah. Okay. So there will be actually we are comparing the um modern physics or relativistic physics, relativistic kinematics, and also the classical kinematics. I want to compare of it is one of it is principle relativity will be one is uh, Galilean kinematics, sorry, Galilean relativity, and also the other is Einstein relativity. Okay, and we want to study about the relative motion of each other, and the big idea of that is quite counterintuitive. Um, quite counterintuitive is the time itself is not it's not absolute for any frame of reference. Okay, let's say you want to measure time in one of the reference, one of the inertial mover or inertial frame. Inertial frame, it measure the time, difference time interval time. Okay, it's not same as the another. It may be not same as the uh, time interval for another frame of reference. Okay, so there will be actually it's a throughout of absolute time with the idea of that when you are dealing with Einstein relativity. Okay. Okay. So yeah, it will be in one of the idea is that you want to from Maxwell equation where you try to derive the speed of light, and you found that there will be the speed of light is constant. Okay. It says that they want to propose the things. There will be the frame of reference. We call it ether. Ether. Okay. Its coordinator is an SRO frame. Okay. So the speed of the light is moving at that frame is in the constant is in that velocity. So they try to find physicians trying to find the SRO frame from the past until the time of Einstein when he proposed the relativity things, and actually it's actors ether uh, and also proven by another experiment also. Okay, proven by another experiment that ether is not exist, and there will be no absolute frame of reference. Okay, based on the postulate also Einstein postulate. Yeah, and we're talking. Yeah, it will be the boost. Okay, yeah, I just okay. So it will be some we're going through the yeah. Okay, so so the idea of that is one of the idea implementation of this. There's some historical point of views on why you want to find the absolute frame, and at the end it's no absolute frame and being replaced by theories. Okay, and you are going through the transformation. Like one of the idea you want to obtain is a Lorentz transformation. Okay, let's say you have a friend, moving friend, S prime. Okay, the moving friend, the inertial frame moving the inertial frame S prime, and also the rest frame S. Okay, so this of you will want to you have the information from one frame, you want to transform into another frame. Let's say you have the information of the XYZ, XYZ, and also the time. Okay, you want to transform it to the S prime, or in another way around, it will be the one of the method you can try on is you can use is Lorentz transformation. Okay, so in fact you go through the books, the what you call the book. Okay, you want to go through the books that you are studying, HRK or HSK for the name. sorry. Yes, and derivation. I'm not sure if in university physics by university physics or physics for engineering and physics. I'm not sure which one of it. Okay, so they are drawing in a classical way. In the usual way, they are drawing a trend and have an object. There is there is throw by an observer. Okay, let's say it's the trend is moving. Okay, in that frame, in that people of field, the ball is when you throw up, it go down, right? So it's going upside and go downside. And in another frame is outside of the people seeing that the train is moving. The ball will move like this. Okay, so there's another kind of derivation also, in the sense that they keep the Einstein second postulate. Okay, so the distance of it. Okay, so the distance of it is sorry, the velocity of it is constant. Okay, the speed of light is constant. Want to derive from to get the equation of yeah. Okay. So another things I want to talk about, I mentioned about Minkowski space-time, right? When we are dealing with the soft flat space-time, because you want to talking about the GR, talking about the curved space-time. Now we are talking about the flat space-time, in essence of gravity. Usually we are dealing with normally we are dealing with the Minkowski metric. Okay, which is you can be found in these kind of equations, and you can go through the derivation of certain here. Yeah, there'll be a derivation. Right, this is the derivation of the Lorentz factor. Okay. In fact, there's we are calling it as another term, we can call it a metric. Metric also, there will be a Minkowski metric. Okay, we are talking about, and also the space-time interval. The space-time interval we want to keep in mind also is it's invariant. Invariant in the sense that in the terms that it's all unchanged on this uh, equivalent way to say it, unchanged for the different frame of reference. Okay, for the different inertial frame. Okay, the space-time interval or the metric stuff. Okay. Want to keep in mind that because now we are usually for simplicity, okay, for the simplicity itself is we are dealing with the one dimension, okay, one space dimension plus with a one time dimension, okay. So we usually call it a one plus one dimension. And you want to deal with and you will further study on and you want to deal with the three-dimensional space and one-dimensional time. So we call it the three plus one dimension or four-dimensional things. Okay, so yeah, we try to separate it. So yeah, we can call it a one plus one dimension. And the idea, you will see that the it somehow is like a Pythagoras theorem. Okay, but then it just itself um the time direction. Okay, the astrophoto, the time direction is a negative. Okay, so in some sense, it's like moving in a different direction. Um, you can uh, that way. But then in some of the books also you want to see there'll be depends on the metric itself how you define. Uh, sometimes they will define, let's say CT, right? CT X Y and Z. They define it as they define this will be plus minus minus minus. Usually in you can keep in mind is you just notice that the direction of the time or the sign of the time is opposite with the space. Okay, So if plus 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 space dimension, it will be the and the time dimension will be the negative. Okay, for the metric. Metric. Okay. Okay. Okay, so there'll be transformation of another way, another things that want to see it also, want to see also the matrix. Okay, the matrix. Okay, the matrix is you want to you have a coordinate. Okay, let's say you want have one partial dimension, two dimension is a one dimensional space and one dimensional time. You want to transform the information of the time. Usually we'll write it as CP X. Uh, you can try to okay. It'll be they're trying to keep that same unit as the length. Okay, so okay, you want to transform from that frame. Let's say this is an X frame, rest frame. Okay, uh, you want to make a transformation. Okay, to CT prime to S prime. Okay, you can view it as a mathematical way. You want to transform the coordinates to another coordinates which you will find in later the linear algebra stuff. And if you want to in physics way you want to think of like you want to transform from the rest frame to the moving frame as prime. So good. Okay. Okay. So yeah, I want to transform the rest frame to the moving frame. You can go through the transformation of the matrix. It's just a multiplication of the transformation. If you call it the Lorentz transformation. For the information, to get a new information. Okay. In mathematical way, in linear algebra, you is yeah, and also in if you're going to you want to have information and not how to say, not restricted to the Lorentz transformation also. You want to do the reflection transformation, rotation transformation. You can multiply the one matrix to get a new coordinate, okay, new info that you want. They are not restricted to the Lorentz transformation so on. But then if you want to be neat on it, the mathematical way you can multiply the matrices. And then you use one. Yeah. Actually the matrices itself is quite useful in the physics in various physics field. So not just the transformation. Yeah, it's quite useful. So I hope that say you can keep the linear algebra because the branch will be a linear algebra. Right? Okay. You want to keep things in mind. Keep that in mind if you want to further study on the physics. Okay, so because there will be three implications you want to familiar on. So you might want to things to realize that the contract length contraction, time dilation, and also the loss of simu simultaneity. Simultaneity. Uh, Keep in mind that it's just the highlight idea is a moving object and moving clocks. And as you can see for the example next on, I will try to explain like why is it not why is it how you apply it in the situation. Okay, for length contraction for moving objects, let's say you have let's say for this example, right, you have a stick. Okay, let's say a stick. just stick. Okay. Here, one dimension. Okay, just moving in V direction. X direction next year. Up in the speed of V. Okay. You want to measure. Okay. Okay, you want to measure the line. Okay. Let's say it's a proper line. Okay. It will be the proper line. Okay. The proper line is like you have let's say you have a two 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 observer. Okay. One of the observer is not moving. Okay. Another observer is moving with the stick, with the velocity v. Okay. So these people measure the length is a proper length. We call it proper length. Okay. Because you see the length itself is the stick itself is not moving. Okay. But then when you see the outside of the observer, see on the stick, okay, it will measure the contract length. Contracted length. So that observer, okay, the outside observer will found that the object is moving. Okay. So we say that we define that we define that we define that if these people seeing the object is not moving, will be measured properly. Okay. Okay. So and also the moving clocks. Okay. Let's say you want to measure a time. Okay. These people. Okay, two people also. Okay. And let's say it's in a rocket lah. Okay. And there will be a clock. Wow. One clock. And I hold one clock. So this observer hold one clock. So initially they synchronize the clock lah before the rocket is moving. They synchronize the clock. And the moving clocks, okay? The moving clock. Let's say this observer see the time of the clock itself in the rocket is moving, right? So the clock is moving and will the clock itself is a moving clock. Okay. If you run slow, we call it time dilation by a factor of gamma. Okay. Okay. In the sense that you want to see on this question, time interval for different friends. First, time interval for your friend, which is at the rest. Okay, your friend, okay, relative to you, the stick friend relative to the stick. Okay, your friend relative to the stick friend relative to you. Okay, which is a 2 for consideration. Okay, so just the want to see. Okay. Yeah, want to track this question. Okay, the first situation, like in your friend relative to you, okay, in your friend relative to you, right, the time interval we will found that it will be you'll see you're trying to measure the length and so on. You define it as length, okay, velocity is equal to distance and time. So we want to measure the length of the time of the okay. Okay. When the stick is like when these people looking at the stick, like the stick is moving. For the moving objects, the line will contracted. Okay, so the line will contracted to a factor of gamma. So we call it L over gamma. Okay, L over gamma, and it will be the time. Okay, the length itself divided by the velocity of the object. Okay, of the object. Yeah, of the object will be the time. Okay. And the second question will be like the stick frame. The stick frame, seeing that that stick is not moving, the stick is not moving. Okay. And relative to the stick type also. Okay. You, in that frame of reference, the stick, the type of the stick. Okay. Because the stick is not moving, so it will be measure length L, and also in her in his clock will be the this one. Okay. The third question is about the frame, your frame, okay, but relative to the stick. Okay, so want to see the time, okay, uh, time of the outside observer from the stick reference, stick frame. Okay, okay. And go through these three questions, and you found that the fourth question, if you measure the contracted length, okay, and also the dilated time. Okay, actually itself it cancel out. You want to try to find the this okay, yeah. Okay, okay. Because you want to recall back the metric that you define, metric space-time interval that you define. You can use it also. You want to impose some constraint, substitute some constraints on some of the situation in it. You will found that you want to use the space-time interval to define the time that measure between the two frames. So initial frame of okay. Okay. By the way, this question you're seeing two ways. And this one you want to see it in the way that mentioned in here. Or you want to try to you will notice that you measure a contracted length and also a directed time, and when you want to multiply it together, you'll found that the the time itself, okay, the the result come out will be cancel out. Okay, it cancel out, which is come together the contracted length and directed time. So we found that it will be the same like the question two. Okay, the time that you measure is same like the question two. It's a two-way to want to use it out. Okay. Okay. Yeah, the two about the time questions. Okay. So um, okay, another idea is that by the way, if you have any questions, just okay, but any in mind, I'm not sure if you can understand. Okay, so this next idea will be about the space-time diagram. Okay, the space-time diagram itself is the one to for 1 plus 1 dimension, the dimension of space and one dimension of time, and we're trying to make the two units in the same, which is try to multiply it by the c. Okay, multiply by c. So, and you will see it's not the usual way that we are look at it in t. How is it? S over x versus t graph, but then it's like the palette, right? So you're trying to interpret the line or the event itself. The event itself, right? Let's say you want to see this event and this event, how is it presented in the diagram? Okay. So notice the time direction is this, like so. The time direction will move up So in the sense that the time is when the object moves from when the lines like you interpret from downside to the outside, downside to the outside, okay, the time is flowing, okay, flow. The time is flow as usual, okay. And also you notice that because it's one dimension, like the S is moves to the right, okay. So you can conclude that it is the object. As the time goes by, as the time flows, the object will move in this direction, X direction. Okay, the idea is that so you will see the clock right, there will be the time start to close. Okay, the time start to close. Okay, the clock start to turn around. Okay, okay, and also we define the line is a road line lah. So different road line. Okay, for this two of the events. Different. And the point itself, we call it as event. And if you want to be specific again, okay, because we're talking about the space-time interval, right? So space-time diagram, right? And the usual things in that you will see about the Minkowski light cone, the light cone. Okay, it defines that three different things. Okay, if you dealing with the dx square, okay, there will be three type of the events that are related. Let's say we have one event. This is the event. Okay, this is the event, and another event is this one, or this one, or this one. Okay, three events, and we say that this event and this event is time-like related. Okay, and if this event and this event is a line-like related, and in this event will be this event is space-like related. In the sense that you want to deal with the causality called 因果论 okay, in Chinese yeah. Causality. Okay, causality. Want to try to find is it the two events is causality related, like this one happened first will cause it this another event will be after that. Okay, you want to see is it so? So if it is a time related events for both of it, okay, time related event, the we will say that these two events is causality related. Okay. And also the one of the paradox also they come up when want to not paradox or our dog want to know that is it you moving approach to speed of light, is it will be violate the causality, like you like the paradox say what you can move backward to the you can move if you move faster than speed of light, okay, you move faster than speed of light, you can kill your kill. Yeah, then you want to see the causality. So the light con. Okay. I think we actually restrict ourselves in one person dimension. Actually, the light cone we want to see is a cone if two plus one dimension is a cone. Okay, okay. Two cones they are connected, but three plus one dimension I don't know how to draw it. Yeah. So yeah, you have the light cone. You see it. But then he zoom a bit delay from yeah. And you know about the linear algebra, right? Some of the linear algebra we, we talk about some vector space, how the vector is defined, and need to follow some rules and just go through a very brief like um Then we have a basis. Okay, you want to check out more, and you can have this video also. It's by triple one power. I find it's a very useful, very visual way to look at it. Also. It's quite amazing to see, have a visual way to represent the map. Linear algebra. There will be a basis. Okay, the linear combination of the basis. Okay, let's say you have this basis, basis, basis. Okay, this basis. Okay, you want to transform into another basis. Let's say you have a basis like this one 1 0. You want to make this one. Okay, you want to transform it to another coordinate to another basis. Okay, yeah. Remember that we can multiply it by the matrices, or we can treat it as a linear combination. Do some of the transformation, and will be the new frame, new coordinates. In the mathematical way, we call it new coordinates. Okay, and this actually in physics way we call it a new frame or reference. This will be the moving frame S prime. Okay, when you're moving approaching the speed of light. Okay, the fraction of speed of light. Let's say the space time, like the space time diagram. Okay, is will be uh, with a certain angle can be defined in this way. Okay, and we want to see one event, like let's say we want to see one event. Okay, okay. Let's say this event, we want to look at this event. Okay, in the S reference frames, we can find it to this. Okay, to this coordinate system. Okay, for another frame of reference is S prime. Okay, if you want to extract the information from S prime frame of view, okay, you need to draw parallel to the y axis. Okay, y axis like this. You need to draw a line. Okay, you extract the information of S prime. Okay, and also you want to draw it parallel as x axis. Okay, this is a new x axis. You remember. Okay, will be the information about city or time dimension. Okay, so yeah, this is how it transform in the geometrical way. Okay, if you want to go in details, you can go in details on this one. So check out the video also. Okay, and so I touched about the idea, the basis. You have this basis, right? 1 0 and 0 1. Okay, I have this basis. I can do some multiplication and plus addition. We can spend is like we can fill in the space of fill we can fill all the space, all the vector space. Okay, it's like this different basis. We can spend the space also. Okay, fill all the space. Okay. And another the visual way you want to try to check out is this one. Mm, you can check out the one of the best. Sure, which yeah, it's explain the DVD in the visual way quite some drawing stuff. Okay, so yeah, I want to check out the outing inside. Mm, mm. So examples, so these paradox. Okay, here will be some paradox. There are people try to just started to apply the spatial relativity. The old people, the ancient people, yeah, that's not. Okay, so the people trying to apply this spatial relativity and found that there's some paradox and actually can be solved also. Actually not a paradox. Okay. can try to tackle these problems also. You just try to carefully apply the uh, transformation, and also want to find it, how to say, because for this problem, for this characters, I want to measure, I want to keep in mind that when this, because uh, it's not how to say, it's including the acceleration, okay, acceleration. So that's why it's not equivalent. The two frame or reference is not equivalent. Okay, so I want to check out this problem also, how it resolve in that way. Okay, so this will be, we try to deal it with the physics way. It's not quite not quite mathematical. Yeah. So if you have the transformation of the transformation just now, Lorentz transformation, you want to differentiate it with respect to the time to make it as infinitesimal, and also the length itself for two frame of reference. Okay. And we try to divide it, because we define it as the velocity as the ds over dt, right? So we try to divide these two equations, and we'll get a velocity, we'll get a Lorentz transformation for the velocity part. Okay? We will find that it's not like the Galilean relativity, like um, okay. Oftentimes, there'll be some misconception about special relativity cannot describe the acceleration objects. But then be it just how to say, it just not it just it can describe the acceleration object. Uh, I try to request it again. Okay, so special relativity cannot describe the accelerating object, but only GR can. And like there will be some of the misconception before, and but then you want to keep in mind that we can use the inertial frame. Okay, we can use the inertial frame. Okay, to describe the accelerating object. Okay, it's not just the constant velocity. Okay, so you can try to focus on that style of purpose. Okay, and but then in GR, but then it's for the special relativity. SR is the special relativity. The special relativity is just we treat the space-time itself is flat. We try to ignore the gravity. Okay, we try to ignore the gravity, and then if you want to um you want to combine the gravity, want to describe the gravity, you need the GR. You need the GR, which is yeah, the general relativity. Relativistic dynamics. Okay, so I want to mention um, some of the people call it, this one is the relativistic max. You can try to check out it also. Is it real? Is it very physical way to call it like this? Is it okay? We call it this relativistic mass, because we call it the length. Okay? We call it, because we are dealing with the relativistic things, like it will be the rest mass. Okay, rest mass is about the m. Okay, and we try to multiply it, comma, the relativistic mass. Is it real or not? You can try to check out these things. Yeah, but then some of the people call it relativistic mass. If you want to try to straighten out, you want to, yeah. And one of the tools we can try to find here. And another way of thinking of it is like the children particles are very, very, very analog. So another things you want to think of is, yeah. And so one of the idea is that want to keep in mind is when you are moving, people are they were saying about the move when the object is move faster and faster and faster, the map itself will be bigger, bigger and bigger. Yeah, in that sense, it sounds in that sense it's actually not quite true. And we want to properly say that when it's like this, the object moving is faster, faster, faster. The energy, okay, the energy is bigger, bigger and bigger. Okay, so in that sense, you count when you count in the internal energy and also the rest energy, you count because it this one is described the these two, right? Internal energy and so the rest energy. So when the object is moving faster, the energy will be bigger. Uh, it's not quite the mass will be bigger. Okay. And also the four vectors. Four vectors, we want to say also another fancy term is called tensor. Okay. Another way to this another fancy way to write it is like you write it in the power sign. It's not power zero, power one, power three. It's just a fancy way to it's just another way to write it. And you will notice that the tensor and vector is quite related, right? When we are talking about the rank one tensor and rank two tensor, uh, it's actually quite related. And people are quite write it right. Usually people write it this way for the vector. Okay, three vector x y z. Let's say we write it in with an error, or we bold it up. Okay, we bold it like a simple bold it, or we want to write in the four vectors form. Usually we write it as we want to write it as a capital letter, or usually people can we also can write it in the normal terms. Okay, normal x just with this new uh, with the what is it with the Greek letter. Okay, you'll find in they write it in Greek letter, and for the vector they write in IJK symbols. Okay, mu b, yeah, this one. And also we define a zero the terms with zero is or with power zero. The terms with zero is the time dimension. One, two, three is the XYZ dimension. XYZ direction. It's now is the space dimension. Okay. So those two want to another way of writing it. I think it's just a optional one you to want to skip this part. Okay. Yeah, inner product, outer product. Okay. Actually, this one we find it very familiar with what we define the space time of this. Okay. So yeah, we need to find this. Yeah. Yeah, you can try to press on your side also. Actually, we have another 9 or 11 dimension in a very small scales. Actually, it's in the based on the string value. Another nine dimension or 11 dimension. Very small scale. Okay, so this is no need French. Okay, so I suppose, yeah, the relativistic effect that brings to the object in the viewing with the astronomical things, astronomical, the big stuff moving. You want try to observe the redshift, okay, redshift of the things. Um, will write this. Okay. Also, the final idea we want to talk about is the equivalent principle. Okay. Equivalent principle is just like when we are dealing with is let's say like we're dealing with the gravity. Gravity is not a force. Okay. Gravity is not a force depends on the equivalent principle. It's just a curvature of space time. Okay. If you are boring during the purpose also like last time I mentioned, you can check out this video again. Yeah, try to check, try to share. Yeah. Okay. So yeah, it's on the crucial space time. I saw the check out this also. You can type. Okay. So yeah, and also usually when we are talking about the after we learning of time direction and also the problem we may want to check out is the muon, yeah, half life of the muon. Okay. It's quite normal the problem. I would say. Quite a beginner maybe beginner friendly. Beginner friendly things. You want to try to check out this question. Okay. Yeah, and also I believe that the relativity things like they are much more than just this one hour because there'll be many fascinating stuff we try to dig in, and in fact that when I trying to prepare myself for this today lecture also, so trying to recall back what I learned, also find that also not okay, uh, many things to learn, also. Many things to learn, many things to being fascinating again for these theories. Okay, try it's a very brilliant idea to try to check out again for the special relativity theories. So yeah, then this will be our lecture. So actually not much to say. So the idea of that, try to bring up the idea of that of mine to you guys to tackle these notes and also the questions. Um, yeah, much more about the docs. So try to deliver to you guys. Yeah, also another way of seeing that, like another things you want to kind of intuitive way of thinking it, but then it's not quite correct, not quite accurate. Um, okay, why the speed of light is maximum? In fact, some of the it revealed by Brian. Brian, I will call Brian. No good as okay. Delivered by Brian. So the direction of you want to see one of the object moving in that velocity. Okay. When the speed is higher, okay, when the speed is higher, the moving clock will be slower. In the sense that we're doing with this diagram, like um, the line will approach the space dimension. Okay, okay. If you keep this constant, okay, we're approaching this, and also the time dimension for the time velocity. Some kind of the velocity is lower, is lower. So that's why when you draw this, like this will be high, will be higher will be higher and this will be lower compared to original list. But then it's just a like, intuitive way to think of it. So if you are moving faster, like if you are moving, or let's say if you are not moving, okay, if you are not moving, is the line is this, okay, original. The word line, okay, is something like this. Okay, you found that the speed of time, something like this. Speed of time is a speed, speed of light. Okay, and when you are moving very very fast, like approaching to the speed of light, and it will be horizontal, near to the horizontal, and the time will be slower. In fact, in the black hole, right, the black hole itself, if you are at the event horizon, okay, on that boundary lah, um, on that boundary will be stopping. The time flowing will be stopping. Okay. But then just an idea lah, don't to talk about it. The talking why is it the realized constant. Sorry, realized density. Okay. Yeah. Okay. So this will be my presentation. I yeah, I won't call it as a presentation today. Okay. So any thoughts, any questions? Thanks for being with us for it, being with me for this 1 hour. Okay. So yeah, I think you'll be just from my part. Just want to confirm again. Uh, have you any questions? If not, I will. Did you have any add on or any to say about before?天妖，青天妖 is 天妖。I think it's 天妖 lah. I think it's most noisy one. There you are. Okay. Okay. So yeah, I think it will be just for um, the presentation will be just ended. Okay. So if there are any questions, you can try to ask them. You can try to ask me also if you have anything you want to clarify, anything you want to ask about, any other stuff to yeah. And thank you everyone for today's. Okay, so all the best for the R4 team. Yeah. And also all the best for the next camp. We will not be around, yeah, but then we'll be around in R4 also. We'll be around in R4. Yeah. And also pre-departure camp for I4 I will be around. I think INS been long. So, yeah. Okay. And see you again.